Good morning, students. I welcome you all in this new lecture. As you may recall that we had already discussed compressors and different types of compressors in refrigerator system. So basically we are discussing the four major components of a air conditioning system, that is compressor, condenser, expansion valve and evaporator. So we discussed compressor in detail in our previous lecture. So in this lecture we are going to discuss condenser and expansion valve. So at the end of the lecture you should be able to become familiar with different types of condensers and their functions, and types of expansion valves and how they work. We may be able to finish these two components in this lecture. If not, then we'll continue it into the next lecture. So first, the condensers and different types of condensers. So as you can see, in refrigerating industry we are basically involved with three broad types of condenser, that is water cooled condenser, air cooled condenser and evaporative condenser. We want to take a look on all three of these in a little bit detail. So these condensers and evaporators are basically heat exchangers in which the refrigerant undergoes a phase change. Next to compressor, proper design and selection of condensers and evaporators is very important for satisfactory performance of any refrigeration system. So these are heat exchangers, so they are basic design, how they are designed, and their thermal design will be discussed in your subject of heat transfer. But here we want to basically discuss the different types and their application. Basically that's what our subject is right now. Since both condensers and evaporators are essentially heat exchangers, they have many things in common as far as the design of these components is concerned. Basically they are heat exchanger. A condenser is a device or a unit that condenses a substance, a gaseous substance, to its liquid state by cooling it. In doing so, the latent heat of the gas or of the substance is given up and it will transfer to the condenser coolant. So basically in case of our refrigerator, the refrigerant is being cooled by the outside air, so the coolant is the air in most of the cases. Condensers are typically heat exchangers which have various designs and come in many sizes, ranging from small handheld size to industrial scale units used in process plants. A refrigerator uses the condensers to get rid of the heat extracted from the interior of the unit to the outside air. Condensers are used in air conditioning, industrial chemical processes such as distillation, steam power plants and other heat exchange devices. Use of cooling water or surrounding air as the coolant is common in many condensers. So basically there will be two types of condensers. One are air cooled condensers and one are water cooled condensers. So that we will be looking into. In HVAC industry, condensers happens to be a topic of great importance. Instead of our goal is to understand the basic principle of it, how does it works, and its applications and different types. That's what we are going to discuss here. So types of condensers. There are three types of condenser used in HVAC industry. The first one is the water cooled. In fact, first one is the air cooled, and then water cooled and the evaporative types. So we will be discussing one by one: air cooled, water cooled and evaporative type, evaporative condenser. So the air cooled condenser, these are the most common one. This is the commonly used in the refrigerator and the air conditioner, room air conditioner, whether split unit or window unit. So as the name implies, in air cooled condenser, air is the external fluid. So in this case, in case of your home refrigerator or in case of your home air conditioner, it is the refrigerant is being cooled by the outside air. That is, refrigerant rejects the heat to air flowing over the condenser. Air-cooled condensers can be further classified into natural convection or forced convection. So if the movement of the air is by nature without using any external means, then we call it it's a natural convection. If we employ a fan to move the air on top of the condenser coil, then we call it a forced convection type. So the condenser uses air as cooling medium to condense refrigerant, is called the air-cooled condenser. If the condenser is located on the outside of the unit, the air-cooled condenser can provide the easiest arrangement. These types of condensers reject heat to the outdoors and are simple to install. Most common uses for these condensers are domestic refrigerators. A great feature of air-cooled condenser is that they are very easy to clean. Since dirt can cause serious issues with the condenser's performance, condenser performance, it is highly recommended that these be kept clear of dirt. Air-cooled condenser is basically made of either steel, copper, or aluminum. So in front of you, these are the examples of air-cooled condenser. One is the natural convective type, and the other one is forced convection type. In the natural convection type, the refrigerant is being circulated in this circuit, and as the air passes, it cools down and it goes from the other side. Similarly, here in the forced type, refrigerant enters in from one end and it circulates the pipe of the refrigerant or refrigerant circuitry and comes out from the other side, while the fan is moving air onto the surface of the condenser. So these are some basic these are some example of air-cooled condenser. So these are the large industrial type, and this is your common household condenser with the fan in it. This is like a window AC, in which this is the condenser and this is the blower, the fan. So the fan, and this is the blower or the fan. So the fan is throwing air onto the condenser and making the refrigerant cooler. So and these are the industrial size of these are the fans, which is sucking air from this end, and then it will go through the pipes of the refrigerant and can convert it from gas to liquid form. So these are the examples of air-cooled condenser. Now next will be the water-cooled condenser. In water-cooled condensers, water is the external fluid. Depending upon the construction, water-cooled condensers can be further classified into double pipe or tube inside tube, shell and coil type, shell and tube type. So it's a double pipe type, or shell and coil, or shell and tube type condenser. So we'll take a look at the examples of each one of them. So this is the example of the double pipe condenser, tube inside tube condenser, double pipe or tube inside tube condenser. So there is a refrigerant tube, the red one, which is inside, and then the blue one is the water tube, in which water is flowing. Cool water from the cooling tower is run in one pipe, and inside it is the refrigerant pipe, which is moving. So this way, hot refrigerant will enter from here and it will get cool and it will come out from this end, and cold water will enter from here, and as it moves up it will become hot and it gets out from there. So cool water from the cooling tower will be pumped from this end. And this is another example of double pipe or tube inside tube. So the outside tube has the refrigerant in it, and the inside tube has the coolant, cold water in it. So cold water will be circulated in this coil in this fashion, while the refrigerant will go on the outside tube. So and the refrigerant will convert from gas medium to the liquid medium and come out from here, and cold water will enter from this side, and it will absorb heat from the refrigerant and come out from the other end, from this end. This is another example of the double pipe type. So this is the outside pipe, and this is the inside pipe in it. So this will do the same function as explained. So a shell and coil type. So the shell normally contains the refrigerant, as you can see from here. So the hot refrigerant will be introduced here, and as it converts to liquid, it comes out from the other end of the shell, and cold air will be going in the coil inside. So the coil has the cooling medium, that is normally water, and the shell will have the refrigerant, hot refrigerant in it, or vapor in it, refrigerant vapor in it, and as it travels down, it will convert to liquid and comes out from the other side. So this is the same example: coil in the shell, water cooled condenser. So this is a shell and tube type condenser. So shell and tube type condenser, this could be single pass or two pass. So this example, it is a two pass condenser. The refrigerant is in the shell. And cold water, you can say, is moving into the pipe. So the refrigerant will enter from here into the shell, and it will come out from here, and this is the head of this condenser. So from here we will enter water or the cooling medium, and it will go one pass this way and second pass this way. It will come out from here. The coolant will go out from there. Okay, so this is this green one is also the same example of a two pass condenser. As you can see, the shell side fluid will be enter from here, and it will come out from here, and the tube side fluid, this is the head of the tube side fluid, and it will be enter from here, and it will go two pass from it will go in from the lower one and turn around and come out from the upper one. So this is how it looks like in actuality, this blue one. Okay, and this is the inside of it. So cold water is entering from here, the blue color one, and it goes around two pass and comes out as hot water on the other side, and hot refrigerant will enter from one end, and it will get cooler and come out from the other end. Now the last one of the condenser is the evaporative condenser. So evaporative condensers can be used inside or outside of a building under typical conditions, operate at a low condensing temperature. So this is more like a cooling tower, as I can see it. So typically these are used in large commercial air conditioning units. Although effective, they are not necessarily the most efficient one, and of course they will be more costlier. So basically what's happening here is that you have your refrigerant vapor in the pipe, in these red pipes, which is coming in, and after getting cooled, it goes from this pipe to the outside, and cold water from this swamp, you can say that, or the tank, is being pumped into this pipe, and it is sprayed through these nozzles onto this refrigerant circuit or refrigerant pipe. So the cold water will absorb heat from these refrigerant pipe, which normally have some kind of fins on it also. It will absorb the heat, and the refrigerant will convert to liquid state, and water will gain the heat, or the latent heat of the refrigerant will be absorbed by the water, and it will trickle down here. So as the water is being trickled down, we have a fan which is blowing air in the upward direction. So this fan will cool down the air again. This fan will cool down the water again as it drops down here. So first the water is being trickled down on the refrigerant. It will absorb the latent heat of the refrigerant, and as it is traveling down, the air will be blowing from bottom to the top. So the hot saturated air will get discharged from here. The cold air is being sucked in, and it is blown onto this water droplets which is coming in, and that it will cool down this water, that is as it is falling down here. So the refrigerant flows through a pipe. Through the spray of water, the refrigerant is condensed. A latent heat transfer takes place throughout the pipe. Throughout this refrigerant pipe, a latent heat is being transferred. Latent heat of the refrigerant is being transferred to the water. So these are basically the three types of condensers, water cooled condensers. And then we looked at double pipe, shell and coil, shell and tube type, and then we looked at the air cooled condenser, the natural convection type or forced convection type. So this is all about the condensers and their type. Next we want to discuss about the expansion valve. The expansion devices, these are also called metering devices. There are various expansion or metering devices used in commercial refrigerating system. The two purpose of expansion devices is to reduce the pressure of refrigerant at approximately constant enthalpy, resulting in a large temperature drop. So basically these expansion devices keep the pressure difference between the condenser and the evaporator. So that's one of their purpose. Regulate refrigerant flow to the evaporator. Regulate the refrigerant flow from the high pressure liquid line into the evaporator at a rate equal to the evaporation rate in the evaporator. So they also control the mass flow of the refrigerant from the condenser to the evaporator, because if you send too much refrigerant from the condenser into the evaporator, then the evaporator will be flooded, and all the refrigerant will not convert to vapor. And if you provide less amount of refrigerant from the condenser to the evaporator, then all of the refrigerant will convert in the evaporator to the superheat or to the gas medium, and the cooling may not be enough cooling may not be produced. So there should be a design temperature that you want to achieve in your evaporator. For that you need a designed mass flow rate into the evaporator. So that is being regulated by this expansion device. So there are several types of expansion devices, but we are going to discuss 5 of them here. So number one is the capillary tube. This is the most common one and the easiest and the cheapest one to use. Used up for refrigerating capacities of approximately 10 kilowatt or less. So it is commonly used in the domestic refrigerators and air conditioners. The second one is the constant pressure expansion valve for system with refrigerating capacity of 30 kilowatt or less. Then there is the float valves. The float valves are normally not used in your domestic application, normally used in large industrial applications, and I will show you a video on this one, on the float valve one. This is basically the function based on the float valve or ball valve, if you are familiar with that. The fourth one is the thermostatic expansion valve, the most popular type of valve capable of providing a wide range of evaporator temperature. And the fifth one is the electronic expansion valve. This fourth and the fifth one, they are basically working on the same principle. The difference between the two is that one is you can say that the controlling mechanism is different. The electronic expansion valve is controlled by a electronic device, you can say that, and this one is controlled by a mechanical device or a bulb containing some other refrigerant into it. So I will show you, I will explain you in the next slide, and I will show you a video on these two also. So moving on, So the most famous one, the most easiest one, is the capillary tube. 1 to 6 meter long, and its dia is 0.5 to 2 millimeter inside diameter. Pressure drops through the tube due to friction and fluid acceleration to compensate for reduction in the average density of the refrigerant as the refrigerant flashes. So as the refrigerant is moving into this capillary tube, its pressure will drop. But for each refrigerator, for each air conditioner or the split unit, there is a particular diameter and length of the capillary tube that you have to use, because if you use a different size or different diameter, that is different length or different diameter tube, then the mass flow rate will differ. So the designed cooling that is required by the evaporator cannot be produced. So normally it is 1 to 6 meter per some, but you can find like 16-inch or 28-inch length of the tube which is available in the market, and the diameter is generally from 0.5 to 1 millimeter or 2 millimeter diameter. So you have to be careful that you cannot just buy any capillary tube and put it in any kind of refrigerator or air conditioner, because they are designed for they are designed specifically for a particular refrigerator or air conditioner. So you have to know what length size and what dia capillary tube is used in a refrigerator before you try to change that capillary tube in that refrigerator. So the capillary tubes are cheap and reliable, but they cannot adjust to changes in the parameters such as added load, suction pressure, etc. You need to install a new tube to get different system performance. They also can be clogged. So the number one disadvantage is that if you want more cooling to be produced by the evaporator, you cannot achieve it with the capillary tube, because it is only designed to produce one refrigerating capacity. It cannot change. It cannot produce another refrigerating capacity. So if you need a larger refrigeration capacity, then you have to use a different capillary tube. The same capillary tube will not produce it. Mass flow rate is determined by a balance point between the capillary tube and the compressor performance. As you can gather, that the compressor is the one which is providing the pressure difference between the condenser and the evaporator. So it is sending high pressure, generating high pressure on the condenser side, and it is creating low pressure on the inside the evaporator. So the length and the dia of the capillary tube determines what will be the mass flow rate into the evaporator, from the condenser to the evaporator. So unless and until you change the compressor, the mass flow rate also cannot be changed. So for a given compressor, there will be always a given size capillary tube that will give you the same mass flow rate, which will produce the same cooling rate or refrigerating capacity. So that's the bottleneck right there. If there is too much or too little heat transfer in the evaporator for the given balance point, the evaporator will be starved or overfed. So moving on, the advantages of capillary tube. Number one is that it is inexpensive as compared to the other types of expansion valve that we are going to look at, and it is easier to install or replace. It does not require maintenance due to absence of any moving parts, as it is obvious. There is no moving part into it, so maintenance is generally not required. Provides an open connection between the condenser and the evaporator, which implies low starting torque requirement for the requirement of the compressor, because there is no moving part, nothing. It is directly connected between the condenser and the evaporator. So compressor does not have to provide extra power to get it started. Okay, so these are the advantages. The disadvantage is it cannot adjust itself, so you cannot have different mass flow. You can have only one mass flow rate through it. Susceptible to clogging because of the narrow bore of the tube, because tube is generally 0.5 to 2 millimeter, 0.5 millimeter to 2 millimeter. You can imagine how small it is. So if some reason if your refrigerating circuit got some kind of condensate into it, either the water vapor or the maybe water vapor generally, or air leaked into your refrigerating system, then it clogs your capillary tube. So in that case you have to change your capillary tube. You cannot clean it or service it in any way. You have to simply change it. Limited to use with the hermetic compressor operating with a critical charge of refrigerant. So normally it is used with the hermetic type of compressors. So this is all about the capillary tube. Expansion valve. Okay, so next we are going to discuss the thermostatic expansion valve. So thermostatic expansion valve is basically controlling the superheat into your evaporator, the amount of the superheat in your evaporator. So this is the evaporator circuit right here. Okay, this is the evaporator circuit. Let me highlight it. These are the evaporator circuit. Okay, these are all the evaporator circuit, and liquid refrigerant from the receiver is coming here, and then this is the suction line to the compressor. So this is the suction line of the compressor, suction line to the compressor. Okay, so the compressor inlet is right here, and this is liquid refrigerant from receiver, or you can say from condenser. Liquid refrigerant from condenser is coming from here. Okay, and then it will go into the evaporator. This is the expansion valve. Then it will go into the evaporator, and it will circulate from the evaporator, and then it will go to the suction of the compressor right here. Okay, so in between I have this thermostatic expansion valve, this steel looking object here, but on top of it there is another refrigerating circuit, the brown one right here. This refrigerant is not the same refrigerant which is in the evaporator. This is a different refrigerant. So what happens is that as the refrigerant is traveling from the condenser through this expansion valve into the evaporator, so it will cool down, it will expand, it will absorb the energy from the surface of the evaporator, and its temperature will rise. So by the time it gets here on the top line here, it will have converted all of it to the saturated vapor, or maybe as it's moving from here it may become superheated vapor. Okay, and then it will go at the inlet of the compressor. So this refrigerant will work on the temperature of the evaporator refrigerant which is coming here. So if it is already superheated coming here, then large amount of heat will be transferred here. So this refrigerant will evaporate. As a result of that, that vapor will come here, and it will compress. It will compress this spring load, and as a result of that, this T connector will be moving down in this direction. T connection will move down in this direction, like that, and then it will open up. So more refrigerant can enter into the evaporator when we are getting refrigerant which is leaving the evaporator, entering the suction of the compressor at a high temperature. So the high temperature will go. So we are getting superheat here, superheated refrigerant from the evaporator here. So more energy will be transferred to the expansion valve refrigerant, and it will compress it. If vice versa happens, if low temperature is reaching here, that means more refrigerant from the expansion valve has got into the evaporator, and not all of it could be converted to superheat. Some of them is still saturated vapor and they are coming here. As a result of that, it will not be able to boil this expansion valve refrigerant. Okay, so it will not the pressure here will be reduced. Okay, the pressure here will be reduced, and this spring load will move up this T connector here, and it will close it, so the less refrigerant will go there. So that is the mechanism. Basically, the thermostatic expansion valve is regulating superheat here, superheated vapor here. If more superheated vapor here, that means evaporator is not getting enough refrigerant here, so it will open up and let more refrigerant go through. If saturated vapor is coming here, not superheated, that means there is enough refrigerant in the evaporator, so in that case it closes it. So let the evaporator absorb more energy from the surrounding surfaces. So that's its working mechanism. The refrigerant boils in the evaporator at temperature T at, let's say, 20 degree Fahrenheit, and pressure of PE, let's 18.4 psi G, until it all vapors and then superheats to TS. So here up to this point it will all become vapor, and then up after that it will become superheat at 30 degree Fahrenheit, which enters the suction line. The fluid in TEV, the refrigerant, the brown one, sensing the bulb, TEV sensing bulb would have a pressure PS of 26.1 psig. So this has a design pressure of 26.1 psig at 30 degree Fahrenheit. So if I get a superheat here, 30 degree Fahrenheit, 30 degree Fahrenheit refrigerant, then TEV will be boiling here. Okay, the difference PS minus PE is a signal directly related to the amount of superheat. So this will decide, PS minus PE will be decide what is the degree of superheat here. If it is superheated already, too much superheated, then this brown circuit fluid will be compressing it downward. This spring loaded thing will press it downward, and more refrigerant will get into it. If it is not 30 degree Fahrenheit here, so it's still saturated vapor coming at, let's say, 25 degree centigrade, then less of it will become vapor, so the pressure here will be dropped. As a result, the spring will pull it up and less refrigerant will go inside it. So that's the mechanism. The pressure PS generated in the sensing bulb by the superheated gas passes through the capillary tube to the top of the diaphragm. An adjustable spring provides the balance of the PS minus PE, 7.7 psi at the diaphragm. So that's the mechanism of a thermostatic expansion valve. I'll show you a video also explaining the same thing. So if you could not understand now, you will understand then. Okay, this is another diagram of the same thing, the same mechanism, but a little better illustrated. If you can see, this is the TXE thermostatic valve, TXV, I'm sorry, this is the TXV, this is its circuit. Okay, right here this is the bulb. Okay, and this is the evaporator, and this is the liquid line from, you can say, condenser coming here. Alright, so same mechanism. As you can see, if the evaporator has a low amount of refrigerant here, so by the time refrigerant reaches here, it will be superheated. This superheated refrigerant will heat up the bulb, this bulb and the refrigerant inside it. As a result of that, there will be large amount of vapors available. It will press this spring loaded this diaphragm, which will compress the spring load, and it will open up this T connector. More refrigerant will enter. If there is enough refrigerant inside this evaporator, so the vapor reaching here may not be superheated, it may be such saturated vapor. In that case, less amount of it will be supplied to this bulb bulb. So the refrigerant inside this thermostatic expansion valve will have less vapor. As a result of that, because there will be less pressure on the diaphragm, it will be pulled up, this T connector will be pulled up, and this opening will be closed, and less amount of refrigerant can go into the evaporator, and vice versa. This is the balance of the pressure it is showing here. Okay, so the load on the evaporator goes up as the load increases. So here you can have different mass flow rate in the evaporator. That is the advantage as compared to the capillary tube. Capillary tube cannot adjust to the requirement of the evaporator, or cannot lower or increase the refrigerant which is passing through this evaporator. But in this kind of mechanism you can. So the load on the evaporator goes up as the load increases and the valve opens, increasing the flow of the refrigerant into the coil. The load requirement drops and the evaporator cools down, the valve starts to close and decreases the flow of refrigerant to the coil. So in this in this way you can control the mass flow rate into the evaporator from the condenser to the evaporator, and you can have different refrigerating capacity in your evaporator. So that's the advantage of this one over the this is the advantage of thermal expansion valve over the capillary tube. If the superheat falls, TS will decrease with the corresponding drop in PS. The forces on the diaphragm are now out of balance and the spring will start to close the valve. If the superheat falls, that is there is less amount of superheat, here, so the diaphragm will go up and it will close the valve. This is how it looks like. If the load on the evaporator increases, refrigerant will evaporate earlier and there will be more superheat at the bulb position. Then PS will increase and open the valve wider to meet the new demand. Where an evaporator coil is divided into a number of parallel passes, a distribution device is used to ensure equal flow through each pass. Due to the pressure drop across the distributor, there will now be a much larger difference between the pressure under the diaphragm and that at the coil inlet. To correct this, an external equalizing connection is taken to the coil outlet close to the bulb position. So this is some external mechanism if there is some error. So this is an external mechanism to overcome this distribution issue. So now I want to show you, there you go, there is another diagram just showing the same thing, how does it work, the mechanism. And next will be the video. I will show you the video, and that will be the end of this section, and then we'll go for the next one.
The thermostatic expansion valve, TXV or TEV, is a metering device designed to regulate the rate at which liquid refrigerant flows into the evaporator. By limiting the flow of refrigerant into the evaporator, the expansion valve causes the refrigerant to drop in pressure. This drop in pressure lowers the saturation point of the refrigerant. Managing the flow of refrigerant is essential to maximize the efficiency of the evaporator while limiting any excess liquid refrigerant from returning to the compressor. The thermostatic expansion valve should be located as close to the inlet of the evaporator as possible on the high side of the system. There are a few components and concepts of the expansion valve that you should be familiar with in order to understand how the expansion valve works. We will start by identifying the refrigerant-filled sensing bulb, which is connected to the top of the power head with a capillary tube. Next we have the diaphragm. The diaphragm separates the pressure of the sensing bulb in the top of the power head from the pressure of the evaporator on the bottom side of the diaphragm.
This is the diaphragm.
Finally, there is an adjustable pressure spring on the bottom side of the diaphragm. To increase the pressure of the spring, the stem should be rotated clockwise. To decrease the pressure of the spring, the stem should be rotated counterclockwise. The pressure of the sensing bulb on the top side of the diaphragm tends to push the valve to a more open position, whereas the pressure of the evaporator, or equalizing pressure, and pressure spring tend to push the valve into a more closed position. In order for the valve to feed in a normally operating system, the pressure of the sensing bulb on the top side of the diaphragm must be greater or equal to the equalizing pressure and the pressure of the spring. Let's look at how the expansion valve regulates the flow of refrigerant into the evaporator. As we've already seen, the expansion valve is equipped with a sensing bulb filled with refrigerant, which should be located at the outlet of the evaporator. This bulb is connected with a cap tube to the power head of the expansion valve. As the temperature at the outlet of the evaporator rises, so does the pressure of the gas within the bulb and the top side of the diaphragm. Once the pressure in the top of the power head reaches a certain point, the diaphragm is pushed down, which opens the expansion valve wider. This allows more liquid refrigerant to be fed into the evaporator. As the temperature at the outlet of the evaporator begins to decrease, so does the pressure within the sensing bulb and the top of the power head. When the pressure above the diaphragm in the power head decreases to a certain point, the valve retracts and the flow of refrigerant is reduced.